Bismillahirrahmanirrahim. Silicon, germanium, and gallium arsenide are the semiconductor of choice for the modern microelectronic industry. Now the question is arises why these three semiconductors are the semiconductor of choice. Fully appreciate why this question requires some understanding of the atomic structure of each of these semiconductors. And it shows that how the atoms are bonded together to form a crystalline structure. The fundamental component of any atom, either from insulator, metal, semiconductors, are the electron, proton, and neutron. The lattice structure, neutron and proton, form the centerpiece referred as a nucleus. An electron revolves in a fixed orbit around the nucleus. This model is referred as a Bohr model. The Bohr model of these semiconductor material is shown in figure, where silicon has 14 orbiting electrons, germanium has 32 orbiting electrons, and gallium has 31 orbiting electrons, and arsenic has 33 orbiting electrons. Keep in mind that the same arsenic is used in semiconductor that is very poisonous chemical agent. For germanium and silicon, there are four electrons in the outermost shell, which are referred as valence electrons. Gallium has three valence electrons and arsenic has five valence electrons. Atoms that have four valence electrons are referred as a tetravalent. Those with there are three are referred as a trivalent. And those with five valence electrons are referred as a pentavalent. The term valence is used to indicate that potential energy, which is ionization potential energy, required to remove any one of these electrons from the atomic structure is significantly lower than that required for any other electron in the structure. Now, the question becomes very clear that why silicon, germanium, and gallium arsenide are chosen as a semiconductor material due to their unique electrical and electronic properties and similarly optical properties as well as supportive electronic structures that cater to very specific electronic applications. Silicons abundantly available and have already established technology make it a staple in microelectronics. Germanium has high mobility and a narrow band gap suited for high speed and infrared applications. While gallium arsenide excel in high frequency and many other electronic for many other electronics or optoelectronic devices. Each of these materials play a vital role in advancing semiconductor technology and enabling innovative across the various fields. Now we discuss further the electronic structure of these semiconductors with respect to covalent bonding. In a pure silicon or germanium crystal, the four valence electrons of one atom form a bonding arrangement with four adjusting and joining atoms, as shown in figure. This bonding of atoms is strengthened by the sharing of electrons, and it is generally referred as a covalent bonding. Because gallium arsenide is a compound semiconductor, there is a sharing between two different atoms, as shown in figure. Each atom of gallium or arsenide is surrounded by atom of the complementary type. There is still sharing of electrons similar in the structure to that of germanium and silicon, but now five electrons are provided by the arsenide and three by the gallium atom. Although the covalent bonding will result in a stronger bond between the valence electrons and their parent atom, it is still possible for the valence electron to absorb efficient kinetic energy from any external source such as light, temperature, or applied voltage, cause to break the covalent bond and assume the free state. The term free state is applied to any electron that has separated from the fixed lattice structure and is very sensitive to any applied electric field, such as established by voltage source or any difference in potential across the thin film material or devices. The external cause include effects such as light energy in the form of photons and thermal energy, which is generally referred as heat from the surrounding medium. At room temperature, there are approximately 1.5 into 10 power 10 free carriers in 1 centimeter cube of intrinsic silicon material. That is approximately 15 billion electrons in a space smaller than a sugar cube, an enormous number. And these many semiconducting properties of silicon inherently depends on the intrinsic free carrier density of the electron.